Okay, I use the bathroom, that doesn't mean I use the bathroom. I totally understand. That's why spring breaks are Okay, perfect. Lots covered, so let's go ahead and get started. So just the announcements, we're inviting you to it's due tonight. Yeah, I think it has one math problem, the rest is Le Chatelier's related, so I try to keep it fairly quick. If you do not turn in your Le Chatelier's lab, it is due at the start of class on Wednesday. I reviewed my lab ed puzzles, and due to the fact that we have changed our pH meters, my lab ed puzzles are no longer valid. So there are no lab ed puzzles for Wednesday. But you will get a quiz. Now it's not going to be a quiz over, it's going to be a quiz over the concept of titrations like you did in College Chemistry 1. So it's not going to be over something that you haven't gone over. But you do need to remember titrations. I will post the homework either tomorrow or Wednesday. And it actually is not due until a week from Sunday because I gave you until the Sunday after spring break to get it done, or the Sunday of spring break to get it done. There are also two math ed puzzles that will be due at the same time on that Sunday, the 26th of March. Now, just a little bit of a heads up, the week after spring break, I will not be here. Dr. DeRocher will be teaching the lecture on Monday. On Wednesday, Dr. Taylor will be proctoring your third exam. And then on Thursday, I have 3 different people taking the lab. The 8 a.m. lab will be taken by Nicole Tamayo, who is our laboratory coordinator. The 1050 lab will be taken by Jamie Freeman, who is our chemical hygiene officer. And then the 240 lab will be taken by Dr. DeRocher. So that just gives you an overview of that information. I will still be posting everything like I normally do, and I will be discussing the topics that they will be going over. I will be writing the exam. I just won't be here. Any questions about all of my announcements? Okay, if not, we're going to get started. So we're getting into the material that we were finishing up with on Wednesday of last week. On Wednesday of last week, I introduced the definitions of acids and bases. There's actually 3 definitions, one of which you learned in College Chemistry 1, and that is an Arrhenius acid is a proton donor, and Arrhenius base is a hydroxide donor. It just so happens that the reason you learned that particular set of definitions in College Chemistry 1 is because you were focused on acid-base neutralization reactions, which one of the products was water. Now, moving on to College Chemistry 2, there are 2 definitions we'll go over. The first one is the Bronsted-Lowry definition. The Bronsted-Lowry definition is a much broader definition than the Arrhenius definition. For Bronsted-Lowry, you have to have a proton donor for the acid, and the base is going to be a proton acceptor. Now, in order for a base to be a proton acceptor, it has to have a lone pair. So you're going to be looking for something like a sulfur group, or an oxygen, or a nitrogen, something that can have a lone pair. The last definition we'll focus on is going to be a Lewis acid base definition, and it's going to focus strictly on the electron movement. But we'll get to that one later on, or Dr. DeRocher will get to introduce, and I'm not sure which. So, on Wednesday of last week, I started introducing these topics. You can take hydrochloric acid, for instance, which is an acid, and it would donate its proton to water to make hydronium and chlorine or chloride. You can take nitrous acid, and it also being an acid is going to donate its proton, and it becomes, since it's working with water, it's going to donate its proton to the water, and it's going to become hydronium and nitrite. You can also mix water with a base, such as ammonia, And if you mix water with the base, such as ammonia, then the water has to act like an acid, and it donates a proton to the base, ammonia, making the ammonium ion and hydroxide ion. And then finally, another example would be where you can take a carbonate ion and mix it with water and make hydrogen carbonate and hydroxide. A couple of things to note about these reactions, though. They are balanced chemical equations, as one would expect, but they are also called charge balance, because if you add up the charges on the left-hand side and add up the charges on the right-hand side, they have to be equivalent. Because the charge is based on an electron, and we're not losing electrons in this particular game. That brought us to the conjugate acid-base definition. Basically, conjugate acid-base pair is anything that differs by a single hydrogen, specifically an H+ group. So if we go back up here, we have our, if we look at the water and the hydronium, they differ by a single hydrogen. Since the water is acting as a base, that means that the hydronium is going to be the conjugate acid. Hydrochloric acid and chloride differ by a single hydrogen. If hydrochloric acid is the acid, that means that the chloride is the conjugate base. We could continue. Nitrous acid, HNO2, differs from nitrite by one hydrogen. Since nitrous is an acid, that means that the nitrite is acting as the conjugate base. And again, the water differing by one hydrogen, that means hydronium is the conjugate acid. We could continue this process and go through more reactions where we are dealing with ammonium. Ammonium and ammonia differ by one hydrogen. If ammonia is acting as the base because it's receiving the hydrogen, that means ammonium is the conjugate acid. And the hydroxide would be our conjugate base. And same thing for our carbonate. The hydrogen carbonate has one more hydrogen than the carbonate, so it's the conjugate acid. And the hydroxide is the conjugate base. Now, the other thing I wanted to make note of, you will notice that the very first reaction had a single-headed arrow. That is because hydrochloric acid is a strong acid. And most folks learn about the strong acids in college chemistry 1. Basically, they are HCl, HBr, HI, HNO3, H2SO4, and HClO4. Those are your strong acids. The majority of the rest of the acids are going to be considered to be weak acids. Strong acids go to completion, hence the single-headed arrow. Weak acids, weak bases, and as we will talk about, some ionic salts don't go to completion. They reach equilibrium, and that's why you have the double-headed arrow. Now, I just wanted to make a note again, so to help you figure out the charge. Basically, if you need to figure out the charge of a conjugate base, you're simply going to add the charge of the base plus, excuse me, that should have been the conjugate acid. Plus the hydrogen. So in other words, that H plus brings with it a +1 charge. That's why in this example of CO32 minus, when it absorbed a hydrogen, we had a +1 adding to a CO32 minus. Well, a +1 and a -2 makes a -1, and that's why we recorded it as a -1. You simply are doing the math. Another definition that you need to know is an amphoteric substance. An amphoteric substance is simply a substance that can act as both an acid and as a base. The first two reactions I showed you, water acted as a base. The second two reactions I showed you, water acted as an acid. Water is an example of an amphoteric substance. It can act as both an acid and as a base. But that's not the only one you would encounter. Another example of an amphoteric substance could be the bicarbonate ion or hydrogen carbonate ion. Here, in this particular case, the hydrogen carbonate is accepting a proton from the water to make carbonic acid. So the bicarbonate is acting as a base while the water is acting as an acid. But because bicarbonate does have a proton attached to it, that bicarbonate can also act as an acid. Where that bicarbonate could lose its proton to water. And so it winds up acting as an acid. So the bicarbonate ion is another example of an amphoteric substance. It's something that can act as both an acid and a base. One thing you're going to find out if you look at it, any of your polyatomic ions that can have two or more hydrogens. Will be the -1 charge will be an amphoteric substance. And in the case of phosphate, the -2 charge will also be an amphoteric substance. Any questions so far? The first part was simply review, and that's why I'm moving through it. Now, something that's new is when we do start talking about acid dissociations, those acid dissociations will occur stepwise, meaning you're going to lose one hydrogen at a time. So for instance, with phosphoric acid, it has 3 acidic protons. The first reaction will lose the first acidic proton. The second reaction, you would lose a second acidic proton. And the third reaction, you would lose the third acidic proton. So again, when you have a polyatomic, polyprotic acid or diprotic acid, those acids are going to dissociate one hydrogen at a time. This will become important in a little bit when we start talking about equilibrium constants. Folks, even though I don't test you over definitions, you got to know the definitions. Because when I write a word problem, I'm likely to use the term. And if you don't know what it means, you're not going to be able to answer the question appropriately. Okay. Let's move on to acid-base. I've already discussed a little bit about the fact that the strong acids are HCl, HBr, HI, HNO3, H2SO4, and HClO4. What I haven't discussed is why. And that is what we're about to do. So basically, with our acids, we can divide them into binary acids and oxyacids. Just as a reminder, a binary acid is going to be an acid that has hydrogen plus one element on the periodic table. An oxyacid is going to be an acid of a polyatomic ion. Now, acid-base strength. If you're dealing with binary acids, the larger the anion, the stronger the acid. The reason, folks, is because an acid is something that gives up a proton. Well, if it gives up a proton, that means, like chloride, it's going to leave behind that negatively charged ion. The bigger the atom is, that negative charge has to reside around, the greater the disbursement of that charge. So again, with respect to the binary acids, the larger the anion, the stronger the acid. Because when that anion loses its H plus, the resultant negative charge is able to spread out more. Binary acid strength has nothing to do with electronegativity, in other words. Absolutely nothing to do with electronegativity. It has to do with atomic size. So since it has to do with atomic size, I'm going to see if we can jog some memories. Down a group, the atomic size. Increases. Because you're adding more shells. Across a period, the atomic size decreases. Because you're not adding any additional shielding, but you are adding more and more protons in the nucleus to pull on the electrons, so you're increasing the Z effective. Okay, oxyacids. When we talk about an oxyacid, again, an oxyacid is going to be an acid of a polyatomic ion. An oxyacid strength increases with an increased oxidation state on the central atom. There's more to it in that these polyatomic ions, they have lots of oxygens. Oxygen loves electrons, so these electrons are allowed to move around the entire structure. But the easiest way, the quickest way to tell exactly who's going to be the strongest acid is to be able to do the oxidation states. The higher the oxidation number on the central atom, the stronger the acid is going to be. So let's look at some examples. HCl, HI, HF, HBr. I want us to put them in from weakest to strongest.
Well, they're all in the same column, so then you just the stronger one to give you larger. HF, HCl, HBr, HB.
That is correct, because these are binary acids, meaning hydrogen and one other element. They're binary acids. The acidic strength is going to increase as you go down the group because the anion size increases. So it would be HI, followed by HCl, followed by HBr, followed by HI.
Put HI first.
Oh, weakest to strongest. No?
Yeah.
Oh, I see what I said. I see what you said. I put HI twice. Then HF. Thank you. Just took me a moment. What about the next ones in line? Selenic acid. Hydroselenic acid, hydrosulfuric acid, and water. It would be the exact same thing. Because water is the smallest, it's going to be the weakest, followed by sulfur, followed by selenium. Okay, let's get into the oxyacids. So who remembers the rule for oxygen with respect to its oxidation state? The -2. Unless it's a peroxide. Who remembers the rule for hydrogen? It's a +1. So for all of these, you know the hydrogen, you know the oxygen, you're just going to be coming up with the one in between. So we have 3 times a +1, so a +3. We have 1 times X, So X, we have 4 times a -2 for a -8, and because phosphoric acid is neutral, it's gonna be set equal to 0. When you solve this, you will get an X equal to 5. For sulfuric acid, again, you know hydrogen and oxygen. -2 + 1. So you have 2 times 1 is 2 plus an unknown X. 4 times -2 is -8. And you set that equal to 0 and you solve and you get an X equal to 6. You continue this, you'll get an X equal to 5 for nitric acid. And for the sulfurous, you're gonna get an X of 5. I gave myself a difficult time. Which one's the strongest? That one's obvious. The sulfuric acid is definitely the strongest of the acids that I have listed here. Because it's the only one with an X of 6. As far as the rest of these goes, that was supposed to be, never mind, this one doesn't have a 5. Because what is the formula for sulfurous acid? Anybody? It's H2SO3. So that would be a +2 X minus, or it'd be a +1 X and a -2, so we'd have +2 plus X minus 6, and so the X here would definitely equal 4. So sulfurous acid is our weakest. And this is for the oxys. Now, as far as this other piece, I just happen to know nitric. I mean, I gave you the 6 strong acids. And nitric acid was one of them, whereas phosphoric acid is not. Now, part of the reason for that, folks, is because you only have 1 hydrogen to give up. So you're talking about a greater amount of negatively charged electrons floating around on 3 oxygens. Whereas in the other one, if you only gave up 1 hydrogen, you only have 2 oxygens to play with still. Just to illustrate. Let me draw these 2 real quick. So you can see what I'm talking about. So if I have H and O3. And if I have H3PO4. Those are our structures. When I pop off this proton, make H plus. The 2 electrons that are in that bond are now going to go over to that oxygen atom. So now what you have is you have 6 electrons and a negative charge on that oxygen. Now, the reason nitric acid is stronger is because these electrons can come in to make a double bond with that nitrogen, which temporarily will kick up that and move it back to the oxygen and move it out to this one. So in other words, what I'm trying to illustrate is that this negative charge can be spread over 1, 2, 3 oxygens. That's why it's stronger. Whereas if you pop off a hydrogen, and you're left with a negative charge, because of those other hydrogens, folks, because of this other hydrogen here, and this hydrogen, it can actually only spread out among 2 oxygens. The more that charge can spread out, the stronger the acid it is. So, to come back, number 1, assign your oxidation phase. They will help. If you have 2 molecules with with the same oxidation state, you have to look at their Lewis structure to determine which one's stronger. The more that negative charge can spread out real easy among oxygens, the stronger the acid is going to be. Because it's all about dispersing that negative charge to the best of our ability. Questions? So we talked about the acid strength of this piece, but I haven't talked about base yet. Here is the correlation for acids and bases. The stronger the acid, the weaker its conjugate base. So hydrochloric acid, we know, is a strong acid. The conjugate base of hydrochloric acid is Cl-. Cl-, therefore, is a very weak base. Now, why is knowing the stronger acid base important? Because when you look at an acid-base reaction, it's always going to move from the strongest pair to the weakest pair. Always. So again, the stronger the acid, the weaker the conjugate base. Hydroxide is a strong base. We know that from college chemistry 1. So water is a weak acid. Because that's its conjugate acid. Sulfuric acid is a strong acid. So hydrogen sulfate or bisulfate is a weak acid. I mean, a weak conjugate base, excuse me. Any questions over acid-base strength? Okay, then we're gonna get into the fun part. We're gonna get back into some math soon. Actually, I like all of it, like nothing. I think this stuff's cool. But I'm excited to get back in there. Okay. So. We've already said that water can act as both an acid and it can act as a base. Because water can act as both an acid and a base, it can auto-ionize. Meaning two water molecules, when they combine, can form hydronium and hydroxide. The equilibrium expression for the autoionization of water would be that our equilibrium constant is going to be equal to the products over the reactants. But since we only include aqueuses and gases, it's simply equal to the products. This equilibrium constant has a specific notation. It is the Kw, standing for the equilibrium constant of water. When we talked about Le Chatelier's principle, we said that the only thing that can impact an equilibrium constant is the temperature. So equilibrium constants often, when they describe an equilibrium constant, they often describe it based on the temperature. Now, if you see an equilibrium constant and a temperature is not listed, assume that it's at 25 degrees Celsius. And if you have an equilibrium constant at 25 degrees Celsius, that means your Kw value is equal to 1 times 10 to the minus 14. So we have our two water molecules that are dissociating to form H3O plus and OH minus. If we were to develop a ice chart or rice table, whichever one you want to call it, it doesn't matter how much of the water you have, because it's a pure liquid, you would have 0 of your hydronium and 0 of your hydroxide though. As water is allowed to progress, you would lose 2x of your water. You would gain x of your hydronium and x of your hydroxide. So that when this reaction reaches equilibrium, you still have liquid water, and since we don't include that, it doesn't matter. You would have x of the hydronium and x of the hydroxide. So using our equilibrium expression and our equilibrium constant that we previously developed, our Kw at 25 degrees Celsius is 1 times 10 to the minus 14, and that's equal to the hydronium concentration times the hydroxide concentration. We just assigned those two concentrations, the variable x, so it's x times x, or in other words, x squared. So when you solve for this, you get an x value of 1 times 10 to the minus 7. Okay, so looking at a scale here. 1 times 10 to the minus 7 is for water, so this is considered to be a neutral solution. Anything less than 1 times 10 to the minus 7 means that the solution is acidic. And folks, when we talk about acidic, yes, you can get a negative pH when we get there. Anything above 1 times 10 to the minus 7 wait, I did that backwards. No, I didn't. Is the base. Wait, did it? This is why I don't like it. Hold on. Yep, I did. Which actually leads me perfectly into my next statement. Even somebody that's been doing it forever. When I deal with scientific notation, it's easy to get confused. What's larger, what's smaller. So that's why we don't deal with that too much. Instead, we like to use the pH scale, which takes scientific notation and puts it into a into regular notation. Anytime you see a negative or a P, I don't care if it's attached to pH, POH, pKa, pKw, POH, I don't care what it's attached to. If you see a P, lowercase, that means that it is the negative log of whatever it is indicating. So in this case, it would be the negative log of the H plus concentration would be equal to our pH. If I have the POH, again, I found that P, and that P means that it is negative log of the OH concentration. We'll talk about pKa later on. And because of the P, it means that it's the negative log of the Ka. Now, the nice thing about turning this into the pH scale is when you do so, a 7 is neutral. Anything less than 7 is an acid, and anything greater than 7 is a base. Break time. We'll go for a 3-minute break.
Okay.
You wanna walk around? You wanna go this way? Let's go this way. Get up and move a little. You coming?
Sure.
She's not either. She's not leash.
Oh,
She had been leashing the entire.
She's like, no, I'm good. It's like, Ed.
That's me right now.
She's like, it's nap time.
We can't read through. Let's just take a look. Let's see, smell it, shoot, throw it again. Go and see how it works. Now go into the problem. You can start.
How much you want to do?
About half of all of them. Chapter 5 was 2, that was the first day. I need to finish my note card, which I have most of the stuff, but I'm gonna write down on it. This is what I'm writing down.
There he is, so you take a picture.
It's literally just the stuff in chapter 1, which is what I'm gonna talk about. I have it set down. In the second part.
You can walk around, if you don't mind. Like, tell me.
I'm actively. Right? Well, I'm doing it.
Oh. Okay, so just to recap, we started this with the definition of acids and bases, and conjugate acids and bases. We talked about the fact that when we have a polychloric acid, it's going to dissociate one at a time. We talked about acid-base strength when we look at the acids and bases. If it's binary, the further down on the periodic table you get, the more acidic it becomes, because the electron that is left over can be spread out further around that bigger atom. For a polyatomic ion, an oxy acid, start by figuring out the oxidation state of the central atom. And if you do wind up with multiple acids that have the same oxidation state, then you've got to draw the structure and figure out, okay, how much can that electron be distributed? The greater the number of oxygens it can be distributed over, the stronger the acid is going to be. Then we talked about acid-base relationship. When we're looking at an acid-base relationship, the stronger the acid, the weaker its conjugate base will be. And when we are looking at a chemical reaction, it always wants to move from stronger acid to weaker acid, stronger base to weaker base. Water itself, as we talked about, can auto-ionize because it can act as both an acid and a base. So when water auto-ionizes, it forms hydronium and hydroxide. That has a specific equilibrium constant, and that's the Kw. Literally, the W stands for water. And when it's at 25 degrees Celsius, that means that the Kw is 1 times 10 to the minus 14. So if you do an ice table and you develop the equilibrium expression and you plug in everything and solve at 25 degrees Celsius, then X, which is equal to the hydronium concentration, which is equal to the hydroxide concentration, it's 1 times 10 to the minus 7. So at 1 times 10 to the minus 7, you're talking about a completely neutral solution. And as you saw, it's easy when you start getting into the less than, more than. You have to really think about it when you're talking about numbers that are extremely small. Who's really bigger? Because I think 14 as a exponent, oh, it's bigger, but it's not because it was a negative 14. So really looking at the hydronium concentration to determine whether a solution is acidic or basic is a challenge, because of the fact that you are having to think in terms of scientific notation, and a very small scientific notation at that. So it's much easier to use the pH scale. And P for anything just simply means negative log up, whatever is indicated. With the pH scale, we're now dealing with values that are going to be mostly whole numbers or 1 to 2 decimal places at worst. You know, so it's much easier to deal with. So when you're dealing with the pH scale, if you have a pH of 7, that means that it is completely neutral. If you have a pH that is greater than 7, it's going to be basic, not base, but basic. Just a slight difference in term. Base means the substance, basic means that it's more than 7. And less than 7 means that it's acidic. Okay. So there's one more thing we need to do before we get into the math of the day. And that is, we need to go back to some basics you learned in college chemistry 1. If I have hydrochloric acid in water, I've already said that that's going to have a complete dissociation to form hydronium and chloride. Now, folks, I want to just take a quick moment. You may see the acid written in this format where you actually see the water. But there's also a good chance you're simply going to see it as HCl aqueous, goes to form H plus aqueous plus Cl minus aqueous. Folks, these mean the exact same thing. So why I'm saying that is because H plus and H3O plus get used interchangeably That's a long word. And I'm letting you know that because if you see an H plus, it's the same as H3O plus, as long as the solution is water. Okay, so now going back to basics. So if I have hydrochloric acid, and let's just say I have a 0.05 molar hydrochloric acid solution. We know that hydrochloric acid is going to dissociate entirely into its ions of hydrogen ion and chloride ion. Now, initially, before we mix everything, there would be none of the hydrogen, none of the chlorine or chloride. But folks, hydrochloric acid is a strong acid. It means that it dissociates entirely. So you lose all 0.05 molar of the hydrochloric acid as you go. And because of our stoichiometry, for every 1 hydrochloric acid you lose, you will gain that amount in hydrogen ion, and you will gain that amount in chloride ion. So what you really have in solution is you don't have hydrochloric acid in solution. You have hydrogen ion and you have chloride ion in solution. So if I want to take the pH of this, the pH is equal to the negative log of the hydronium or H plus. Again, we use them interchangeably. So the pH of this solution would be equal to the negative log of 0.05. Which comes out to be 1.30. Now, yes. Did I hear something coming? Now, what if I ask for the hydroxide concentration? What you have to realize, folks, is again, this is really taking place in water. Now, before I get into how easy it is to calculate the hydroxide, let's think about what's going on. You have hydrochloric acid in water going to break apart to form the hydronium ion and the chloride ion. But you also have the autoionization of water going on. To form hydronium and hydroxide. So when I'm asking you for the hydroxide, what I'm really asking about is, okay, so how much water is allowed to dissociate? With the acid concentration being controlled by the hydronium from the dissociation of the acid. Again, what I'm asking you for is how much water is allowed to dissociate. Given the fact that the hydronium concentration is being determined by that strong acid. So since I'm asking about the water, what is my, it's a, it goes to equilibrium. So I use my equilibrium expression. For the hydronium and hydroxide. So that 1 times 10 to the minus 14 is going to be equal to the 0.05 that came from the acid times whatever water can dissociate in those circumstances. Which comes out to be 2 times 10 to the minus 13. So again, yes, the acid did dissociate, but there's also another reaction that's going on underneath it all. And that's the autoionization of water. But the autoionization of water is going to be controlled by whatever else is in solution. Now, just like I asked for the pH, I can also ask for the pOH. What does P always mean? Negative log. So we're looking at the negative log of the OH concentration. Which is a negative log of 2 times 10 to the negative 13. Whoops. Really. Which comes out to be 12.7 or 12 point, excuse me, 12.70. Now I can get to the pOH 2 different ways, folks. There's one other way we could use. You'll remember KW is equal to 1 times 10 to the minus 14. If I want the pKW, that would equal negative log of 1 times 10 to the minus 14, which is going to come out as 14. For our 0.05 molar hydrochloric acid solution, we determined the pH is equal to 1.30, and we determined the pOH is equal to 12.70. When you add these two together, what do you get? 14. So what you can't, another way to get to the pOH is using the equation 14 is equal to the pH plus the pOH. Again, it eliminates that chance of having to work with scientific notation if it's not your favorite thing to do. So before I do another example, I want to make sure we kind of take all these equations and put them together and when to use them. This might be something you want to star, square, have on a separate sheet of paper or whatever, because these are the equations you will use a lot for strong acids and for strong bases. So we're going to say we're going to use the, well, you'll use them pretty much for everybody actually. So we're just going to say acid base. The very first one, pH was equal to the negative log of the hydronium concentration. You use it when you need to get to pH. Skip a section, because I want to show you something, but well. I'm gonna go ahead and put it down and then I can show it to you in a minute. If you look at the inverse on your calculator of the log base 10, you will see that it is 10 to the power. So all I did was move my negative over and then I took 10 to the power. You can use this to get to the hydronium concentration if you're given a pH. Another important equation that we've been dealing with is the equilibrium expression for the autoionization of water. This will allow you to convert between hydronium and hydroxide. So if you know one, you can get to the other. We dealt with the POH, which is the negative log of the hydroxide. And that's if you're gonna, that's just one way you can get POH. And just like with pH, I can move the negative over and then use the 10 to get rid of the natural log. So I can go from POH back to OH minus concentration. And then the last one allows you to convert easily between pH and POH. Which variation of all these equations you need is strictly dependent upon what you need to do, what you're given and where you need to go. And you're going to use these equations a lot, no matter whether it's with strong acids, strong bases, or whether you're dealing with weak acids, weak bases. You can use these equations quite a bit. Let's look at calculate the pH of a 0.2 molar sodium hydroxide solution. What is sodium hydroxide? Acid base. Base. Strong or weak? Strong. So sodium hydroxide is a strong base. So sodium hydroxide is going to dissociate entirely into sodium ion and hydroxide ion. If you start out with 0.2 molar sodium hydroxide. When it's all said and done, you've lost all 0.2. So you gain that amount in sodium and you gain that amount in hydroxide. So there will be none of the sodium hydroxide actually in solution. Instead, you have 0.2 molar in sodium ion and 0.2 molar in hydroxide ion. We can determine the POH is equal to the negative log of the OH. So that's equal to a negative log of 0.2. Which comes out to be equal to 0.6, might as well 0.7 by the time I round everything. So I can get to the pH, which is what I was asked for, by going through and saying, okay, 14 is equal to the pH plus the POH. So 14 is equal to our pH plus 0.7. So the pH has to come out to be equal to 13.3. And because it is greater than 7, it is definitely basic. Just a reminder from College Chem 1, strong acids. Are HCl, HBr, HI, nitric acid, sulfuric acid, and chloric acid. Your strong bases are your group 1 hydroxides. Calcium hydroxide, strontium hydroxide, and barium hydroxide. On Wednesday, we're actually going to pick up and we're going to start with me giving you problems to do. And then we're going to move on to weak acids and give you some problems to do. So it's going to be problem based. Bring your calculator. Because there's not going to be much in the way of lecture. It's mostly done now. It's now on to the detail of calculations associated with everything I've been saying.
That's it. I'm not seeing it. I learned